Hello everyone. I'm very sorry that due to visa issues, I cannot be present to interact with everyone on site. I hope you understand. Our paper, Automated Task Scheduling for Close and Deformable Body Simulations in Heterogeneous Computing Environments, discusses accelerating physics simulation via heterogeneous computing. Physics simulation requires a large amount of computation, and a single device is difficult to meet the computing needs. Therefore, people seek to the help of multi-CPU, multi-GPU, or heterogeneous device. However, heterogeneous computing has the following challenges, including high communication latency between devices, and the latency is usually much higher than the computation time of a single task. And in previous work, we need to carefully design specialized task allocation strategies for each heterogeneous device and each task pipeline, which was not conducive to the universality. However, in fact, the optimal allocation of tasks to heterogeneous devices is an NP-complete problem, so manual allocation strategies might become completely impossible. And in physics simulation environments, the computation of tasks will change with the contact between objects. So scheduling needs to consider dynamic load balancing. And last, the iterative tasks in simulation are usually executed completely serially. So we first address the major problem, how to efficiently schedule tasks in heterogeneous environment. We have tried many solutions including simple average thread segmentation, multivariable linear programming, etc. Finally, we chose a method proposed in 2002 called HEFT, which stands for Heterogeneous Earliest Finished Time. Although this method appeared earlier, it is very suitable for our problem. And we are the first to introduce these methods into computer graphics. Given the dependencies between tasks and the computation metrics of each task on each device, we can finally create a scheduling map which represents which time each task will be executed on which device. We take the calculation process of XPPD as an example to demonstrate the calculation process of HEFT. Firstly, we use DAG as needed to represent the dependencies between tasks, such as broad-face collision detection that need to be completed before narrow-face collision detection. Then we perform topology sorting on the DAG, which generates an ordered list that ensures the dependencies between tasks. Based on the ordered list of topology sorting, we calculate the rank U value of each task. Rank U quantifies the dependencies of each task. If a task has more subsequent tasks, it represents a higher degree of dependency. Finally, we traverse the task list sorted in reverse order of rank U and calculate the earliest finish time of each task on different devices. We use the device with the smallest EFT value as the inserted device. Tasks with higher value of rank U will be prioritized for scheduling, thus minimizing the delay of data transmission to the greatest extent possible. So why is the HEFT algorithm suitable for our problem? Because the algorithm is universal enough. HEFT can be easily extended to other computing pipelines as long as the dependency relationships of tasks are given, which allows for scheduling without the need for other adaptations. In addition, the algorithm is efficient enough. As HEFT is a heuristic algorithm, the cost of executing a scheduling is less than 0.1 milliseconds. Therefore, for simulation tasks, we can dynamically adjust and reschedule the computation metrics based on the actual execution time. This figure shows the curve of ideal scheduling time and the actual running time after rescheduling each frame in 100 frames. It can be observed that two times are very close and the computation time is much smaller than that of the single GPU execution. Then we need to address the second question, which is how do we handle iterative tasks that are almost entirely serial? For example, for XPPD, we need to perform many Gauss-Seidel iterations, each iteration requiring serial traversal of different constraints and different color blocks of the same constraint. Of course, constraint within the same color block can be executed in parallel, but the parallel granularity is too small to warrant further splitting. To enhance the parallelism of Gauss-Seidel iteration, we employed a asynchronous iteration strategy, which allows for certain degrees of overlap in the timeline. However, using this asynchronous iteration directly results in poor convergence of the system. Therefore, we made a lot of optimizations to maximize the parallelism and the convergence rate of asynchronous iteration. Firstly, we integrate these numerical iterations into the Heft scheduling framework so that we can fully utilize the advantages of automatic scheduling framework such as automated load balancing and dependency relationship assurance, allowing us to focus on the parallelization and the decomposition of the iterative tasks themselves. Then we design and evaluate task overlap strategies with varying degrees of inter-iteration and intra-iteration asynchrony and summarize the overlap strategy that satisfies both convergence and parallelism requirements. However, although this overlapping strategy allows for higher parallelism between iterative tasks, when calculating the rank queue of each node based on DAGs, the distribution of rank queue for different constraints is not very balanced due to the cumulative effects. As shown in the figure, it can be seen that a large number of collision iteration tasks are aggregated together on the timeline, utilized resulting in poor coupling between collision constraint and stretching constraint. Therefore, we propose a simple but very effective way to recalculate rank queue of iterative tasks, which is to use a fully serial iteration process DAG to calculate rank queue of iterative tasks. This ensures that different types of constraints are distributed more evenly over time, therefore ensuring that the solution of different types of constraint is more balanced. In addition, as the heft is a heuristic algorithm, if the execution time of a single task is too short, the scheduling time may be more likely to fall into local optimum. Therefore, we propose to perform a certain degree of task merging in the process of topology sorting to obtain better scheduling results. Finally, we summarize the potential data flow between devices, design and compare different data transmission and data weighting strategies, such as taking the average of relative displacement or the average of position, etc. The results shown that taking the average of relative displacement is the best solution. In the end, we set up a faster convergence rate than synchronous iteration methods, while also having higher parallelism, which allow us to allocate iterative tasks into different devices for computation. We validate our method in different scenarios and devices and achieve an acceleration ratio of 300 to 500% compared to CPU implementation and 40 to 80% compared to GPU implementation on M3 Max SoC chips. In addition to XPPD, we have also tested our heterogeneous scheduling framework and synchronous iteration under some cutting-edge nonlinear iteration processes and have achieved certain acceleration effects. Although our approach demonstrates the potential of heterogeneous computing in physics simulation, there are still many directions worth further explorations. Although heft and asynchronous iteration algorithms are hardware independent, we have not further evaluated them on other heterogeneous platforms such as independent graphics card that exchange data through PCIe's due to our current GPU implementations being based on metal shading language. In addition, extending our task to multi-GPU computing environments and real-time preconditioning techniques or other general computing scenarios are also some very promising research directions. Our code has also been open sourced, and we hope everyone to join the exploration of heterogeneous computing. Thank you for listening. Sorry again for not being able to come offline to face-to-face communications with everyone.